Swayam Prabha. Digital India. Educated India.
So, let me start with one example. Let us assume this water is pure water. It does not have any dissolved gas or minerals or something. Okay. So, if it is a pure water, in this bottle, you see still two things: pure water in liquid form and the vapors here, because it is closed. So, I will give back this water, otherwise she is keep thinking, say, where sir will put. I will draw here. Let us assume this is a water bottle and it is in liquid state. It's pure water, okay? No dissolved gases or anything. But still, this liquid water or H2O liquid will vaporize, and we say water vapors or gas. We can write vapors or gas. Why it is not escaping? Because lid is closed. It is a closed system. After certain time, when the space is filled, pressure will generate and it wants to go back. So, this process will start this side. One component, because only pure water is there, but two different forms. What are the two different forms? Liquid and vapor. Liquid and vapor or liquid and gas. How long this will, from liquid to gas, it is called, what is the process called? Vaporization. From vapor to liquid, what is the process called? You can see somewhere might be written here, okay? It is here. How long this continue? Any idea how long this will continue? How long it will continue? Many books says until it reach equilibrium, okay? Okay? But that is not true. Why it is not true? Let me say this way, it is true also and it false also. It is confusing, okay? Until it reach equilibrium, the rate of vaporization and condensation is different. But after reaching equilibrium, both rates are same. So, it won't stop. It stop at equal rate. We assume it stopped or we think it is stopped. What is the difference? Until it reach equilibrium, the rate is different. But once it reach equilibrium, both are same. The rate of vaporization, the rate of condensation. And then we feel it stopped. And that is where, to explain you in a easy terms, they say it stop at reach equilibrium, which is not really true. The real truth is, after attaining equilibrium, both are at equal rate. Now, component how many? Only liquid, only water, H2O. How many different forms it is? Two. So, we call two phases. So, one component, two phases. Now, the question comes, what is phase? If I ask you question, what is phase? What would be the answer? Just try. Wrong answer is allowed. Anybody from first row, second row, third row? What is phase? State of the matter. Okay, good try. Anybody else? Huh? Yes, try. Mechanically separable of heterogeneous systems. Good try. So, state of the matter is not the complete answer, because if it is only pure water is there and I am taking in a beaker and it is in open system, I can't say it's a two phase. So, to tell the phase, to define the phase, at least I should have two different entities. Yes or no? Two different entities, and within that entity it has to be remain same in terms of chemicals, or what we call chemically it should have existing uniformity, and that word is called homogeneous. So, the phase is called homogeneous part of an heterogeneous system. Homogeneous part of a heterogeneous system. What is heterogeneous? You have more than one. What is homogeneous? Throughout it's same. Okay? If I say this class, all are boys, all have same height, same weight, same date of birth, same knowledge, okay, same clothes, everything is same, then I say it's a homogeneous. I pick any boy, everything is same. Okay, when I say two homogeneous part, let's say half of the class are boys, half of the class are girls, but all boys born same day, same height, same weight, same knowledge, same dress, all girls born same day, same height, same weight, same kind of rubber band, everything is same, but still they are distinguishable, boys and girls. But within the girls you pick anyone, all other things are same. That's where we call homogeneous. Why I called heterogeneous? There are boys and there are girls. You understood? So, the phase is homogeneous part of heterogeneous system. Now come back. How you behave in the class, same boy, okay, it's a classroom, one boy we take, how the boy behave in a group of more boys when teacher is here in the class. Okay, second scenario, he is in the class but teacher is not there. Third scenario, he goes hostel, how he behave in his room. Fourth scenario, he goes home, how he behaves, if his dad is there at home, if dad is not there at home, and nobody is at home. The person is same, the behavior is different. Now, to know how a one person behave, it depends the circumstances. It depends what other boys are available or how many numbers of other people are available. And the same way, here the equilibrium or these things behave differently when the external entities are different. Who are the external entities which can affect the equilibrium? Temperature. If temperature is same, we say thermal equilibrium. Pressure. If pressure is same, we say mechanical equilibrium. When I say mechanical equilibrium, pressure must be same, I am silent on other things. When I say thermal equilibrium, I say temperature is same, I am silent on other things. If it is in chemical equilibrium, I told three equilibrium, thermal equilibrium, mechanical equilibrium. If it is a chemical equilibrium, what is same? Can anybody read this? Mu. What is that? Chemical potential. Chemical potential is same. But when I don't say anything and I say it is in equilibrium, it is understood that all three are constant because they affect. If it is not pure, If it is not pure, if it is other thing is there, let's say in this water bottle, she had glucon D powder or Coke or something else. If it is a mixture, let's say coffee. Coffee and coffee means how many things would be there? Coffee. Anybody? Coffee powder, if it is instant coffee, okay. So coffee powder, sugar, milk, water, and on top of that they put some cocoa powder, something they put for taste. Huh? If you go coffee day, they put cocoa powder, something like that for taste. You don't know? Come on. Cappuccino you go and order, you will get it. On top little bit. Now, here it's not one thing. There are many things. Let's say you put this hot coffee in a thermos flask. Okay? External things are not affecting, but internally there is a space, vaporizing and condensing, vaporizing, condensing, vaporizing, condensing. If you have 100 different flasks, same company, same quantity, same person make coffee, but amount of sugar is different, amount of milk is different, amount of water is different, amount of coffee powder is different, the taste is different, and the equilibrium states are different. Even though you keep temperature same, pressure same. Why? I gave an example of boy, how the boy behaves when other surroundings are there. Now, how a chemical entity or how a boy behaves based on the other entities are surround. That's where we learn how chemical potential is different when surroundings are different. You understood? So, this is called partial molar properties or the chemical potential. How chemical potential will change which affect the equilibrium. Entire chemical industries are based on that, where heterogeneous systems are there. It's a complex. So, by keeping out of, let's say cocoa powder I am not writing because you said you don't know, okay. Out of 4 things, keep 3 things constant. Let's say coffee powder, sugar and milk is constant. I keep on changing water concentration. I'll add 1 cup of water, 1.5 cup of water, 2 cups of water, 2.5 cups of water. Taste is different, but here equilibrium will be affected. If we say overall property is a taste, how taste is changing by changing water, keeping 3 things constant, or how taste is changing, keeping remaining 3 constant and milk changing, or keeping the last 3 constant and sugar changing, or last 3 constant and coffee powder changing. This is called partial molar property. In a mixture of multi-component, how one individual component will affect the overall property, it is called partial molar property, and the summation of all partial molar property is affecting, then we will say the differential properties. You got my point? We will see, slides are there, okay. Let me start with this. So, we understood phase, we understood component, we understood equilibrium, and equilibrium will be affected by this. Here, one more thing it will affect if it is not pure. Here 4 components are there. So, temperature will affect equilibrium, pressure will affect equilibrium, chemical potential will be the same at the equilibrium, okay. It will not affect this, but it will become same. But what is the third thing will affect the equilibrium when it is more than one component system. When it is a multi-component system, the third parameter comes, we call concentration, we call molarity, we call molality, but in a chemical equilibrium term, we say mole fraction. What is the symbol? Anybody knows mole fraction? We write small x. Okay. Let's say this water has alcohol also. Let me write methanol. Methanol formula CH3OH. Now it has how many components? 2 components. How many phases? Still 2 phase only. Now this water and methanols are there in a liquid and it will be there in gas also. And it reached equilibrium. Slightly complex, okay, not little more complex. Earlier only water vapors. One component, 2 phase in equilibrium affected by temperature and pressure. Chemical potential is same. Earlier how I should write? Mu water, or I will say liquid water, H2OL equal to mu H2O gas. What I should write further? At equilibrium. At this was earlier case. Now I had water and methanol in liquid and water and methanol in vapor. How to write now? One more term is getting affected. So earlier it was only temperature and pressure. Only temperature affect the equilibrium, pressure affect the equilibrium. Now mole fraction also affect the equilibrium. Mole fraction of what? Water or methanol? Both. You change water also, equilibrium will get affected. You change methane also, equilibrium get affected. But let us say we have fixed mole fraction 50-50. 50-50 means what is x1 and x2, or what is x of methanol and x of water. When I say 50-50, what is the value? 0.5. Because it's a ratio. Moles of a component divided by total moles. And the summation would be always 1. If I say here x of H2O plus x of methanol, what is the answer? 1. Because summation of, because it is only 2 components, summation is always 1. Summation of all composition in the system is 1 or 100%, we say 1. Let us say I fixed 50-50, 0.5, 0.5. Temperature fixed, pressure fixed, mole fraction fixed, and it has reached equilibrium. I want to write mu equation. Can anybody write? This was for earlier case. Now anybody can write the second? You got what I am teaching? You understood, no? Now, how many equations I can write for chemical potential? 2. What are they? First one is true. That itself is true. The second one, mu of CH3OH liquid is equal to mu of CH3OH vapor. What chemical definition says? Many students will get confused here. When multi-component mixture is in equilibrium, chemical potentials are same. This is a half line. What is the full line? Chemical potential of the same species in a different phase are same. You have to write down. In an equilibrium for a multi-component system, chemical potential of the same species in a different phases are same. Not, I cannot write like this. Let's say mu of H2OL is equal to mu of methanol gas. I cannot write this. I cannot write. In certain cases it may happen, but theoretically I cannot write it. But these two are true. You understood? In a multi-component system where more than one components are there and still they are in equilibrium, okay, but only the same species in different composition are same. Let's say I add third one. Can anybody say another alcohol? Ethanol, methanol already. Okay, methanol I will put. C2H5OH. Is okay? And here also C2H5OH. Now, how many components? 3 components. How many phase? 2 only. Here assumption is they are miscible in liquid, they are miscible in gas. Okay, if it is not happening, then phase will be more. Okay. Now, how many equation I can write for chemical potential? Okay, what could be the mole fraction 1? I have to add one more. Plus XC2H5OH equal to 1. This one I have to write. I can add third equation. What is that? Mu of C2H5OH liquid is equal to mu of C2H5OH. Here is the beauty. In chemical industry, when they synthesize any products, we call process and product design. The calculations are very, very tedious, but it becomes easy because we know if it is in equilibrium, chemical potentials are same. So they have reactant 1, reactant 2, reactant 3, catalyst, solvent, emulsifier, coagulant. Huge, it's a heterogeneous system. But they maintain the concentration, they maintain the temperature, they maintain the pressure, so they understand chemical potentials are same and they calculate for a optimization. What is optimum? Optimum. Neither minimum nor maximum. It is called optimum. The process is called optimization. And for the optimization, the process, this chemical potential is the key in understanding for process and product design. Did you get my point? Okay. What is the optimization here? Any chemical industry, what they want, one line, can anybody say any business? Whether it is any business or let us focus here on chemical industry. What they want? What they want? Any chemical industry, what they want? If it is a business point of view, minimum investment, maximum profit. You agree? If it is a chemistry point of view, minimum reactants, maximum conversion or maximum yield, no byproduct. No byproduct, 100% yield. And to minimize the amount of reactants required or to increase the yield to 100% or to decrease the byproducts, the process what we fix, the temperature should be how much? Close to room temperature. Minimum is also wrong. Maximum is also wrong. Pressure should be how much? Close to atmosphere. Why? That's the easy. You need not to pay money. How much stirring is required? Minimum. How much time required? Minimum. Because we want always more, the product. And this process is called optimization. And most of the time, optimization of the complex system can be understood more easily when you know the chemical potential concept. When we started, it looks so simple. Now imagine you have 10 liquids, 10 vapors. 10 chemical potentials are same. Means you get half of the information free. What is the condition? It should be in equilibrium. Okay, you got my point? Now, I gave an example of only liquid to vapor. Is it same if it is solid to liquid? Is it same if it is gas to plasma? Or is it same directly solid to gas? Answer is yes. You want to ask any question? Answer is same. Any equilibrium, when you only condition is they should be in equilibrium. Now you understood the beauty of the chemical potential. We will go in more detail, okay? We will go in more detail. Should I rub off this? So let me start my class. This was a trailer, okay? Movie is not started. Now we will start. So we will study about phase equilibria. Now you understood what is phase, what is equilibria, isn't it? What is phase? Homogeneous part of a heterogeneous system. What is equilibrium? What is equilibrium? The rate of conversion of one phase to other and the other phase to the one, both are at the same, at constant external parameters like temperature, pressure, and if it is a multi-component system, mole fraction also the same. Okay. I took the topics for you from the syllabus of UGC, CSIR, JRF, and also the GATE. So if you would like to write JRF exam or the GATE exam, these topics would be useful. So I chose the topics from there. Okay. So at the end of this class, you should able to understand these four things. One, chemical potential and its significance. In the trailer itself, I told a little bit. We will tell more. And then, what is ideal and a non-ideal solution? It's only about liquids. Okay. What is ideal solution? What is non-ideal solution? And how to understand these phase transitions. Phase is changing from one phase to other phase like solid to liquid to vapor. How to understand? And what we will get to know with that. And then see, anywhere when phase change occur, so many properties significantly change. For example, you are in the class, you go to hostel, same person. The change would be so huge, you have to here obey a nice dress, well combed and everything. Once you go hostel, you would like to be relaxed. So the phase has changed from attending in the class and staying at home. The many of the attire will change. The way you sit, it will change. Same way for any chemical species, when phase change occur, so many properties significantly change. And that's where it's become complex to understand why it is happening so. And that's where we try to understand, even though with this much complexity, is there anything is easy to understand? Is there any rules? Anybody try to understand that rules? We will see phase diagrams. So a diagram which shows different phase. You can also put your diagram. I am in class, I am at home, I am in this one, I am in a playground. How you? And take one property. For example, my hairstyle. How it change? Or my shirt. Something like that you can say, and then try to draw. You will get a something new picture. Imagine how it can be drawn. Okay. And then we will apply some rules, Raoult's law, and then Clapeyron equation, Clausius-Clapeyron equation, and then we will go forward. So this much you will understand in next 1.5 hours. The easiest way I start, let's say, what is a solution? I put an example already there. Solute plus solvent is a solution. Usually, solvent is in a large portion, solute is a small portion. Okay, and then we say when make a uniform mixture, homogeneous mixture. If they separate out, we can't say solution. If they separate out, let's say water and rock, sand, we will not say solution. Okay, it has to be uniform. Okay, composition has to be uniform, or it should be miscible or dissolved or soluble. Okay, I'll take a pause for a while. Can you calculate this? Just to give a in between break, calculate. Can you calculate this? What is the question? Calculate the molarity of pure water. Density is given, molar mass is given. Pure water, if it is, this is pure, what is the molarity? Anybody? Molarity of a pure water. What is the molarity definition? Moles per liter. Yeah. Density, if you don't want to use also, no problem. You want to use also, no problem. Centimeter cube is ml. Centimeter cube is ml. So, if I say density, what is centimeter cube? If I draw a cube of length, breadth, height, all are 1 centimeter. So, this will be called 1 centimeter cube. In that, you see the cuvette, no? In that, if I pour water, how much water it can go in? Fill. That is 1. So, how much it is? Water is 1 gram. If I put this cube and pour water, 1 gram of water will go. Can you convert this? This is a second question. First question I am asking. 1 gram per centimeter cube is equal to how many kilogram per meter cube? Quickly you try. Any answer is allowed. 1? Try, try. Rough notebook you try. Try. Wrong answer is okay. Without trying you are telling. 0.001. One answer somebody told 0.001. I don't know. Let us see if it is true or not. Anybody got other answer? 1 gram per centimeter cube is equal to how many? So, if I make a cube of 1 centimeter height, 1 centimeter length, 1 centimeter breadth, amount of water I can pour is 1 gram. If I change this, I don't know, 1 meter, how much big I should draw? 1 meter means very big, no? Let us assume this is 1 meter. This big cube. In this I am pouring water. How many kilograms it will go? Not grams. Only one answer so far. Wrong answer allowed, Amma. Tell me the wrong answer. If you tell right answer, I will stop. Wrong answer you tell. 0.001. Okay, good. Wrong answer. 0.01. Good. That is also wrong answer. Oh, I asked you to wrong answer only, no? 0.0. 0.1. That is also wrong answer. Good. 1 is also wrong answer. Good. Huh? 100 is also wrong answer. Good. Okay, 0.0001. Good. This is also wrong answer. All are wrong, okay? All are wrong. So many guess you did, okay? Can you prove 1000 is correct answer? Can you prove 1000 is a correct answer? Try. Otherwise, we are not going. So it's at least when I say try, you should put head down and pen, no? Huh? Yes or no? When I say you try, at least you should put head down and pen and try to write something. You got 1000 answer? You get up, you help him. 1000 you got? You got? Okay, show to him. See, 1000 he got. You only told, huh? 1000 you got? No, you just showed. You got 1000? See, in this. 1000 you got? Okay. Chalo, we'll go forward. Okay. Now you do this. I assume all of you got 1000. 1000 is the right answer. Okay. How many wrong answer you told? Chalo, next. Molarity of water. We have to teach so many things. I mean, here only. How? Try. Wrong answer is also no problem. You try. It should not be one way. I be keep teaching and you will be keep listening. No, you also tell me something. One is the wrong answer. No, wrong answer. 0.1 wrong answer. Wrong answer. Okay, I am showing you the answer. Let us see. Okay. So, moles of what we have to write? Mass is the same here. So, in the 1 liter, if you assume density is 1 liter you assume it is 1000 gram. That's where density is given. So, 1000 divided by 18 is the answer. 1000 divided by 18. What is the assumption here? Density is 1. That means 1 gram and 1 ml is same. Okay. 1000 divided by 18. What is the answer? 55.55. 55. It continues. Was it a difficult? Then? Or you all are BSc or MSc? Okay. We'll do one more example and then I will start teaching. Okay. Calculate the molarity of silver nitrate, what we call AgNO3, that 3 should be denominator, okay. That dissolved in water to get a final volume 250 ml, quarter liter. Silver nitrate molecular mass is 170 gram per mole. This question is not for GATE or NET. This is not even for BSc. It is a 8th class question. 8th class. Why I did it, sir? You may say, sir, we are MSc. Why are you insulting us with 8th class? I thought just for a break. So you can put some pen and a notebook and then we will go to the next. Okay. Anybody got answer? We have to calculate molarity. So, molarity's definition you should write. Number of moles per liter. So, grams is given and molar mass is given. So, 6.8 grams means how many moles? 170 grams means 1 mole. So, 6.8 means how many? You don't need even calculator, but calculator is allowed. You can use mobile. Mobile means calculator, not ChatGPT. You can use mobile, not a problem. Means calculator you use. 0.16 you got, okay. So, 6.8 gram means 6.8 divided by molar mass, it is around 0.04 mole. 0.04 mole by 0.25 liter because that is 250 ml. ml you have to convert into liter. So, the answer will be 0.16 moles per liter or 0.16 molar. Okay. Now, should I go forward? We will come back to this one more question later on. Two more questions are there, I will tell at the end. Let us start. Chemical potential. So far what you understood chemical potential? So far I told only one line. At equilibrium, same species chemical potential is same in two different phases. This much only I told. Yes or no? What I told? A chemical species, same chemical species in one phase and other phase, if they are in equilibrium, chemical potential is same. Now we will try to understand what is chemical potential. Chemical potential is any energy, any kind of energy per mole. Okay, but you find most of the books only gives free energy. Only gives free energy you will find, not other kind of energies like enthalpy, Helmholtz free energy. Why? Anybody can answer now? By seeing the definition you will understand. How to write? Mu. Why I put I? If you remember in my example in the trailer, we took H2O, then we took CH3OH, then we took C2H5OH. It can be any. So I can't write any, so I am writing I. I means any kind of species in a mixture. Okay, mu I is equal to dou G. Why dou? Why dou? Small change. Okay, dou G by dou Ni. Please remember this I and this I is same. What is N? Mole. Mole. N. What is G? Gives free energy. Now, what is this denominator here? T, P, N, J is not equal to I. Let us try to understand this equation. Okay? Let us assume our first example. Three things are there. H2O, CH3OH, C2H5OH. So here I can be H2O, I can be C25, CH3OH, I can be this. So 3 times I can write this equation. How many times I can write this equation? Depending on how many species are in the equilibrium. Where did I say equilibrium here? Yes. How I said it is equilibrium? How I said it is equilibrium? T is constant, P is constant. Not T and P. Many other things are also I said it constant. How I wrote? J means this is J, this is J, this is J, this can be I, this can be J. When I say this is I, remaining all are J. When I say this is I, remaining other are J. When I say this is I, remaining other are J. So other than I, all are J. Okay? So this, if I want to write in 3 times, how I will write? Mu H2O is equal to dou G by dou N H2O T P N NCH3OH NC25HOH. Can you write remaining 2 other terms? Now you understood what is the significance of this equation. How many I possible? What is the I number? In my example, 3. So if my I are 3 different species, here it will be 2. If my I have 10 species, How many will come here? 9. You remember the coffee example? Huh? Coffee, sugar, water, milk. Okay. So here 4 are there. So here 3 constant. Remaining all other things have to be constant. And this is what we understand the chemical potential. Everything has to be remain constant. Only one thing you are keep changing. If I want to know how loud or how low this boy's volume is, I have to ask everybody to be silent and ask him to speak. Then how much he can disturb the class, I understand. Let's say 2 boys are talking. How much disturbance happening to the class because of those boys? It's only possible when all others are silent. If everybody is talking, I can't say the disturbance to the class because of those 2 students. It's difficult. So, here we understand each species energy per mole. Energy per mole. Now we say this is constant. You understood, no? This is constant if in 2 different phases are there. How easy it become calculations. So complex things were there, it becomes so easy. And that's where we can have process and product design plants, calculations. This is the one of the most important and fundamental thing in physical chemistry to understand chemical potential. Okay, let us go forward. If it is gas, we have to write in terms of pressure. If it is a solution, we have to write in terms of activity. If it is a generic form, we will write like this, chemical potential. So, chemical potential can be also written in terms of pressure or in terms of activity. Nothing but this is another form of concentration or telling the moles. This is what we wrote. Okay. Now, if it is in equilibrium, let's say this value of a solution, we said mu I H2O, mu H2OL is equal to mu H2O gas. But for mu H2O, we have 2 equations from here, and both will become same. Then you see if the standard conditions are same or not, or how you get the standard conditions. This becomes so easy now to take it forward. Okay, but I am not going into that. Okay, let us try to understand why G only. This question I asked, we didn't discuss. Okay, is it another energy possible? Can we define chemical potential through another energy? Answer is yes. But did you see any book other than Gibbs free energy? Most likely no. There are very, very few books which talks about other kind of energy. Why? Why? If you see here, you understand. T and P constant. In a laboratory, when you want to do experiment, keeping temperature constant, keeping pressure constant is relatively easier compared to keeping other things are constant. What are the other things? We will see. Volume constant, or the moles constant, or entropy constant. That is also possible, but more difficult. Error may be more. Keeping temperature constant is easy. Keeping pressure constant is easy, relatively. That's where people go only for Gibbs free energy. By definition, any energy change per mole is a chemical potential. If it is mixture, if it is pure, molar energy is a chemical potential. Let's say there is nothing else, only water is there. There is nothing else. Nothing is constant here. Only water is there. What I can write? G by N. Mu is equal to G by N. Or we will write mu is equal to Gm. What is Gm? What is Gm? Molar gives free energy. Is it true or not? It's true. It's true for one component system. It is true for pure system. So this is only for pure or one component. So only water and water vapors are in equilibrium. I can say molar gives free energy of water and molar gives free energy of water vapors are same. You remember with which I draw this in the beginning? Liquid and vapor. This is liquid and this is vapor. Both are H2O. Only one component. If they are in equilibrium at constant temperature and pressure, I can write molar gives free energy of H2OL is equal to molar gives free energy of H2OG. From where to where we are going, you see. Not only molar gives free energy, you can apply this equation here. You can talk about activity, you can talk about pressure. What is the condition? They should be in equilibrium. Now, if this and this is same, okay? This partial molar quantity and this is same. Only thing is F is written as a G here and alpha and beta variables are written here T and P. Both are same. But if I change this to another energy, for example, internal energy. What is U? Can I write chemical potential in terms of internal energy? Yes. What will change? This constant parameter will change. So, you have to keep entropy and volume as a constant. If I want to change this to U. So, you can write this. First is this one, then you write the second. Chemical potential in terms of G, chemical potential in terms of U. What is changed? Whom we are keeping constant is changed. Why? Then only you can attain the equilibrium. Then only you can understand the species, how it affects. Because your energy term is changed. Or it is coming from the variable. U is natural variables for internal energy are volume and entropy. Can I write in terms of enthalpy? Answer is yes. But you should keep pressure and entropy constant. Can I write in terms of Helmholtz free energy? Answer is yes. But you have to keep volume and temperature constant. So far you are thinking chemical potential only through G, which is not true. But easy to understand through G is true. The reason is laboratory keeping T and P constant, relatively easy keeping S constant or V constant. And that's the reason all books, instead of telling all kind of energy, they say let us go simple. Now, how you will define chemical potential? Any energy change per mole of a given species, keeping remaining all species concentrations are same and still they are in equilibrium. If you want to understand in different phases. If you don't want to understand equilibrium, but you say change per change of energy per mole or energy change per mole is a chemical potential. Okay?
Swayam Prabha. Digital India. Educated India.